So speaking of things in the future, a little bit of house cleaning. This class sequence is not coming back until the fall of 2019. If you like me so much that you can't imagine not having me in your lives next fall, I am teaching a class that is listed as CLDP 948, which is Latent Trait Measurement and Structural Equation Models. It is cross-listed with the EdPsych version of SEM, which is EPSY 906. That class was offered last fall using R. My version uses M+, but otherwise the material is exactly the same. And I know some of you already had that class, and rather than take it again or lose the information forever, for those folks, I would actually recommend an advanced seminar that's being offered in EdPsych as 980, which is going to be a Bayesian psychometric modeling course. So it's latent trait Bayes style, which means he'll have to go back over the ML versions of everything. So if you need a little bit of review, that would be useful for that too. So if you have any other questions about coursework or things, what would be good for you to take given your interests and your research areas and the classes you have had, I'd be happy to chat with any of you. Just as an aside, I'm not covering it in this class, but if anybody wants to learn how to do meta-analysis via mixed models, I have stuff for that. I'm happy to give you examples. It's surprisingly straightforward. It ends up being a special case of a two-level model where level 1 residual variance is fixed and separately estimated or separately specified, for each study. But otherwise, it looks exactly like the same proc mix code you already know. So I noticed there's a course on that here. I'm saying I can show you how to do that as well. So that's that. Let's see. You have a homework that I'm guessing no one has started, and that's totally fine. I hope you all had some kind of break. I heard, Erin, you said, I took Tuesday off, right? That was you. Okay, I heard someone say that over here. Did everybody take at least one day off? Erin didn't. Well, just, I appreciate the need for break because you're sharper if you give yourself a chance to recover. So I hope everyone took at least one day off. Weekends are included. I understand that the weekday-weekend distinction is not necessarily relevant for everyone. But does anyone have questions on Homework 5 if you have looked at it? Not yet? Well, it is due a week from today. So rather than having it due on Friday as traditional, I wanted to give us one extra day for questions if they come up. It is on the long side, so it's a 14-pointer. I think it might be my longest one yet, but it's clustered data. It uses the same type of setup that we did in example 6. So a couple of twists, though, that I want to make sure you're aware of, which are in the instructions. One is that I am asking you to write the code to create group-level predictor variables. So normally I give you all of the variables that you need, and you just have to center them or recode them. In this instance, I want to make sure you know how to create group-level variables. The code to do so is in the front of example 6a. In SAS, for instance, you can use proc means. The by statement then asks for a mean per group, and this out statement here saves those means to a new data set specified here, and you can rename the variables accordingly. And if you're more comfortable working in some other program to do data manipulation, I don't actually care how you do it. I have code to do the same thing in SPSS as well as Stata in this example. The other small catch is that in this example we had a binary level 1 predictor, and so I left it uncentered. And so everything in here was phrased as within school effects and contextual effects. In your homework, I'm asking you to do group mean centering instead, so you will have within effects and between effects. Because I'm asking for interactions, those will be easier to work with, and that's why I asked for it that way. And one other thing, I did add something to this example that I wanted to point out that I think may be useful for us at some point. When we switch over, I added the final model using M+. So this handout already had Stata and SPSS as alternative software packages. The last model here is an M+ as well, because we will get a chance to see their between and within syntax, which is necessary if you want to do any kind of multivariate multi-level modeling, such as mediation, any kinds of things. So I wanted to give you some more examples with that, and since I had this one already, I went ahead and added it. So that last page is new. I made a note on the syllabus that I had updated this handout today. So that's that. So, any questions? Well, I had initially thought that we might need to do a little bit of reviewing as a separate topic, but we did some of that last time, and we'll end up doing that in the context of our new topic, which is all the stuff that you already know, plus what to do with not normal outcomes. Are you ready? I've already had my requisite caffeine today, so I'm hoping to calm down as the class proceeds. I'm a little wound up at the moment. So we have then a brand new lecture, Lecture 7, Generalized Models. So there's a lot of vocabulary that goes into this that is different and can be intimidating if you don't know what it means. The books on these topics, I think, are much harder to read as a consequence of the extra vocabulary and extra notation. So I want to hit some of that just to begin with, so that when you do see it in documentation or in other books, it's less unfamiliar to you. So that's the first thing here. So then reviewing. Let's go back to two-level data. Let's do a longitudinal example first, and then the first generalized example I have will actually be the same cluster data set. So this is what I would call an unconditional growth curve model, or unconditional model for time. Let's say that we have 4 occasions, and I have a random linear time slope fit to those 4 occasions. Then the way that we would describe this model, the words that you have learned and the letters and such that go with them, this would be a general linear mixed model. So breaking apart those terms, general means all of the residuals in the model are supposed to have a normal distribution, because that's the likelihood function that we're using. Linear means that it is linear in the parameters, meaning that it's intercept plus slope times variable plus slope times variable plus slope times variable, even if those variables themselves are nonlinear, things like quadratic time, for instance. That's what linear means. Mixed means that it has both fixed effects and random effects. And then model means what you think it means. So everything that we've done so far, the variants of the multi-level model or hierarchical linear model, you can call those that, these are general linear mixed models. So we would say that we have at level 2 a G matrix that looks like this in this specific example. More generally, it holds the variances and covariances of the level 2 random effects. So we almost always have an intercept, and then we have some kind of random slope for a level 1 predictor. So in this case, this tau squared sub U1, what is that thing right here? It goes with this thing right here, U1. Random slope variance. Now we need some more words to be extra specific, right? That's the level 2 random time slope variance. So time is a level 1 predictor. Its effect can vary randomly over level 2 units. So the variance itself is a level 2 parameter. What it is the variance of is a level 1 effect. So that's where the level terminology gets confusing. Random things always vary over at the level above. So if you can have a level 1 predictor, it can vary, its effect, can vary randomly over level 2 units. So we have our intercept variance, we have our random slope variance, and they get a covariance by adding type equals UN to the random line. That covariance is not the default in SAS or in any other mixed model program, interestingly enough. That's something you always have to add for reasons that I don't understand, other than maybe job security. At level 1 then, that's our R matrix of level 1 residual variances and covariances. This R matrix doesn't have any covariances. If we have type equals VC, which is the default, and which is what we usually end up with in most of our cases, the residual variance is the same over time, and there is no covariance among the residuals. The reason that this is plausible is because all of the reasons for different variance over time and all of the reasons for covariance over time of the occasions within a person are over here in G. So it's not that the occasions from the same person aren't related, it's that they're not related anymore after you factor in each person's intercept and slope and how those differ across people. Those terms create patterns of variance and covariance. And if you put this model into one equation, which you will see sometimes instead of this sort of placeholder notation, the beta 0 intercept would be a combination of this fixed intercept and this random intercept. The beta 1 is a combination of this fixed linear time slope and the random linear time slope. Each of those gets multiplied by the time variable. And then E is the time and person-specific residual, whose variance is supposed to be the same across times and persons. So all of this is review, right? Feel comfortable with this? Reasonably so? So if we were to start with an empty model, and I add a fixed effective time in an empty model, which of my two variances would it explain? Level 2 random intercept or level 1 residual? You know this one. If I have level 1 time, which variance does it explain? Level 2 random intercept or level 1 residual? Not a trick, I swear. Level 1, yeah, level 1 time at a minimum will explain level 1 residual variance. We can calculate a pseudo R-square and see how much it goes down. Now, foreshadowing, the reason we do that, the reason we can do that, is that residual variance is a separately estimated parameter whenever we're assuming a normal distribution. The normal distribution has two separate things that characterize it, a mean and a variance. A multivariate normal distribution, which is what we have here for 4 occasions from the same person, would have, for instance, 4 means, 4 variances, and 6 covariances. But the point is, the variances and covariances are separate from the mean. One does not determine the other. In the models we're heading to, for non-normal outcomes, that may not be true. So for instance, in binary data, there is no such thing as an estimated residual variance anymore. That means we can't do a pseudo R-square for it. So we have level 1 time explaining level 1 residual variance. If time is purely level 1, then what will happen to the level 2 random intercept variance as a consequence? If time is purely a level 1 variable, it only has within information, what happens to level 2 random intercept as a consequence? Up or down? Up. What happens if time has some level 2 between information in it? Then random intercept variance could go down, and that's when you have to worry about smushing, meaning that the level 2 variance in time could have a separate effect than the level 1 variance in time. That's a cohort effect. That's the accelerated time models that we started with way back when. If I were to then, after adding my random linear time, let me back up here. So if I add random linear time, do I calculate pseudo R-square? If I add random linear time, so now I've added fixed time, I'm now adding the U1 here. Do I calculate pseudo R-square for our new random thing? Nope. Do random effects explain variance? Nope, they make new piles. They reallocate variance. In this case, we would be saying part of what we thought was level 1 residual, why are you off your line today, is because some people need different lines. So part of what we thought was level 1 residual variance is actually specific to a person-by-time interaction. It becomes a level 2 term. It doesn't explain anything, though, because we still don't know why each person needs a different line. We just know that they do. What do I do, though, to test whether or not I need that random linear time slope? Fit test, yep, otherwise known as, let's hear some synonyms. Model comparison, keep going. Likelihood ratio test, give me another one. What's it called in SCM, for instance? The same idea. The thing the -2 log likelihood difference is distributed as? Chi-square, yes. The chi-square test of model fit in SCM, for instance, that shows up by default. That's a specific type of likelihood ratio test of your saturated model versus the one you fit. You'll also hear that called a deviance test. Yeah, those are all the ones I can think of, but that type of thing shows up frequently. What's the deal with Emel and Remel and likelihood ratio tests? Do you remember that? If you're testing random things, you use a likelihood ratio test, and you can do that either using Remel or using Emel just fine. That's the preferred way. If you are testing fixed things, if you want to test model improvement due to a change in fixed effects, then which estimator do you have to be in to do it via likelihood ratio test? It's ML, yes. But if you're in Remel and you don't want to switch over, but you do want to test the improvement of a set of fixed effects, what can you do instead? That's an effect size. That wouldn't be a significance, but that would also be relevant. Specific instances include an omnibus main effect in ANOVA, a change in R-square, the F-test for your R-square like in regression. What's that thing called when you test multiple fixed effects at the same time? Starts with an M. In the first word, we'll play hangman. Second word starts with a W. Hey, multivariate wall test, yes. So regardless of which estimator you're in, you can always do univariate and multivariate wall tests. If you want to test whether new random things improve your model, that's a likelihood ratio test also in either ML or Remel. Let's see. What else do I want to say about that? What's it called when we put G and R back together again? V, yes. So this same thing, which is in this like nice, friendly Calibri font, also looks like this in books, including mine. If you want to describe those equations more compactly in a matrix form, it would look something like this. This is the way that the stats books that cover generalized linear mixed models will write this. And so I want you to see this and recognize that you know what this means, because it can look intimidating. So this is exactly the same as this. So I'm writing this per person. If I have 4 outcomes for a person, I have a y vector that looks like this. X is the name of the place where all of the predictors that have fixed effects are stored. In this model, there are 2 predictors. We count the fixed intercept, which is the column of 1s, and linear time, which is the column next to it. Depending on your book, sometimes this gamma right here is going to be beta. Given that I use the gammas for fixed effects, I used gamma up here to be consistent, but beta is probably more common. This is the place where your set of fixed effects is kept, one for each column in X. So here we have gamma 00, that's my fixed intercept. Gamma 10 is my fixed linear slope. So these two red things right here. Z is the name of the place where any predictors that have random effects goes. So X and Z both hold predictors, but they don't have to be the same, because not all predictors that have fixed effects can or should have random effects. So that's why they list them with two different letters. X holds the predictors that have fixed effects. Z holds the predictors that have random effects. And so in this model, both intercept and linear time have random effects, and so that's why we have the same thing here as here. U then are the individual specific random effects whose variances are the model parameters. So U0, random intercept, U1, random linear time, and then E, 4 E's, in this case, one for each occasion for each person. And so if you do the multiplication, it quickly starts to look just like the bottom here, where you have fixed plus random plus fixed plus random. So you can reorder these however you want. Here it's fixed and then random. Here it's fixed random, but it's the same idea. So in red, model for the means, fixed effects, the part that everybody gets. In blue is your model for the variance. Random effects and their covariances plus residual variances and covariances. Here's how we get V out of that. It's the Z matrix, which again is just the matrix that holds the predictors that have random effects, times G, times Z flipped over on its side, or Z transpose, plus R. So because the G matrix gets wrapped around by two Z matrices, that's why I say it's not really G plus R, but it's G and R combined. Okay. Are you with me so far? So now new words. If you were to take this version, what we're doing here, the same model, and see it in a stats like hardcore stats book, they would have sentences that say things like this. The marginal distribution for Y, meaning everything that goes into the prediction, fixed and random and everything else, we would say that Y is distributed normally with, and whenever you see this normal thing, that means mean variance in that order. Mean is given by X gamma, meaning conditional mean. Meaning mean is whatever the model for the means and the fixed effects say it's supposed to be given your predictors. So that front term here is the idea that each person and each occasion gets, each occasion in this model, because there's no person predictors, gets a different predicted outcome based on a linear model. If we had people-level predictors, it would be different for each person too. But anybody who has the same combination of predictor values would have the same prediction. So it's conditional, meaning that it's conditional on predictors, but it's part of the means model, the fixed effects, meaning that people don't get their own. It's only your own based on your predictors. And then where the variance goes is V, because that's what this model says, how we get the variance. It's the V matrix. It's G and R put together. It needs to know which effects are random and what kind of R matrix you've put across the observations from the same level 2 unit. Conditional, then, is another specific kind of distribution. And note the change in what is considered part of the mean side. This is an important change for the models that we're going to look at for non-normal outcomes because they're all phrased this way. The random effects get counted on the mean side. So the term that you will see in the books and the term that I'm going to start trying to say more consistently is linear predictor. The idea that after controlling for both fixed and random, the only variance that's left over is due to R. So we would say that Y has a conditional normal distribution. That after controlling for fixed and random, R can be described by a multivariate normal of whatever specification you've picked. This combination of the fact that Y has the same type of distribution both marginally and conditionally means that maximum likelihood is relatively straightforward. Every model that you've run in here, no matter how old these computers are, right, up until homework 7 where we had, or homework, what was it, not 7, 4, right, where you had cross models, everything ran within a half a second, right? Boom, done. That's because of this property. That's not going to be the case once we move out of normal land. So this idea of a conditional distribution then, we're going to switch terminology from level 1 residual, which is what R used to have, to conditional distribution. So it's not that the level 1 residuals are going to have alternative distributions, it's that the conditional distribution is an alternative. And this is hella confusing in terms of the terminology. But if you think about like a binary outcome, right? What are possible values of Y if you have a binary outcome? 0 or 1. So what we will say in that case is that the conditional distribution for my binary outcome is Bernoulli. It's not that the level 1 E's are Bernoulli. They can't be. It's that once you control for the fixed and random effects, then what's left in terms of the last single level, the level 1 outcomes, that's Bernoulli. So models that are generalized, which is where we're heading for non-normal outcomes, they differ because they have a non-normal conditional distribution. You can think of it as the level 1 part that's left over after you have the fixed and random effects, but that's not technically correct. So I'm going to try and not say level 1 residuals anymore because they don't exist anymore. This is a distinction that starts to matter once you leave normal land. So we're going to be talking about, instead of saying that this conditional distribution is normal, what should it be given the kind of outcome that you're predicting? Outcomes that are bounded by either 0 or 1 or some other value can't possibly have a normal conditional distribution. So what else could it be? The good news is that there are lots and lots of choices already built into software. So I will show you how to do multi-level models with other kinds of conditional distributions in Stata, in SAS, and in M+. Unfortunately, I will not be able to show you how to do them in SPSS because SPSS, as far as I know, the last time I checked, only has quasi-likelihood estimation. So we're not going there. So putting all of this new terminology then together. So general linear models then, that's the term that you use for what you would used to call regression in ANOVA. It's when you have one observation per sampling unit. You don't have levels. It's a single level model. And the conditional distribution is normal. This is the only kind of model for which you can do any kind of least squares estimation. So this idea of like sums of squares and mean squares, this is the only situation in which any of that matters. Ized linear models, those are single-level models for not normal outcomes. So their conditional response distributions are something other than normal, such as logistic regression. That's a Bernoulli conditional distribution. count regression. That's usually some kind of Poisson or negative binomial or something like that. But they still only have fixed effects because it's single-level data. Those are the types of data sets you would use those models for. We spent the last, 9 months or so on general linear mixed models. The conditional distribution, meaning the distribution of the level 1 residuals that's left over, is normal. We have both fixed and random effects. And these models are appropriate for outcomes that are continuous, meaning they, in theory, could go from negative to positive infinity, and we don't have to worry about keeping our prediction within some sort of plausible scale. Once your outcome has a boundary on it, on one side or the other or both, that's when we're in the world of generalized linear mixed models. So IS means some kind of not normal conditional distribution. So after controlling for fixed and random effects, what does the distribution look like for that outcome? Linear, meaning slope times variable plus slope times variable. That's all of these models are like that. Mixed, meaning fixed and random effects, meaning that we have more than one level of sampling. And link functions then go into this idea of some kind of not normal distribution, because the link function is what we need to keep our predictions within the boundaries of the observed outcome. So I should have brought it in, but I've been looking at Walt Stroop's book again. It's called Generalized Linear Mixed Models. And because I'm such a nerd, you know when the first time was that I read that book or tried to? It was on vacation. I took it to the pool with me. And I remember someone walking behind me and looking over my shoulder, and she's like, "Are you reading math?" I'm like, actually, yes, because I'm that big of a nerd. But that book was super hard for me, and I think it's the easiest of the ones I've tried to read. And I've been trying to reread it and get myself acquainted with all of this terminology. I'm not going to lie to you, this shit's hard, okay? It is. It's everything, like I said, that you've already learned about multi-level models, plus all of this at the same time. So we'll go slow. I want to try to keep the big picture in mind of what these models are for, and then hopefully you can come back to the nuances of how to fit particular types of data with the big picture in mind, because that will make it go easier. So big picture, it's still multi-level models. It's still the idea that we have a sampling plan with at least 2 dimensions to it, such as over time and over people, or over people and over groups, or multiple combinations thereof. Anytime you have sampling that's more than one dimension, you need more than one kind of error term, more than one kind of variance. That's when you have fixed and random effects. You want to be able to keep your predictions within the scale of the outcome that you're predicting, and that's where link functions, which we'll do in just a second here, and conditional distributions other than normal come into play. All right, how are we doing? Okay. So these are more types of models. Each of these types of models has a particular set of what's called a link function, which is going to be a transformation of the outcome, and the conditional distribution that goes with it. So we'll start with binary. Why does everybody start with binary? Because it's the easiest. And because it's fairly common, particularly in fields like public health, or I know the sociology folks, you guys have a lot of like sort of logity kinds of stuff, right? So we'll start there. All of the stuff that you learned for binary is then reused for categorical outcomes, either unordered, which is known as nominal, or ordered, which is ordinal. There are models for counts. That's your Poisson negative binomial family with a log link instead. Censored data, that's Tobit. Zero inflated, those are either hurdles or some kind of zero inflated distribution. We'll have a little bit of that at the end. And then there's also models for things that are continuous but that aren't normal. Like response time, for instance, is almost always skewed. There's a gamma distribution that can work well for those. So there's all these distributions out there that are already built into software that you can use to try and figure out what would make sense given the scale of your outcome. So there's 3 parts of these models then. Only one of them, I'd say one of them you know already, and the other 2 are new. So first, non-normal conditional distribution. After accounting for the fixed and random effects, what is a plausible distribution given the scale of the outcome? Why this matters is the standard errors for everything you care about. If you have the wrong model for the variance, meaning the wrong distribution, those standard errors are likely to be incorrect. Sometimes, depending on which family you're in, you won't actually have an estimated variance for your conditional distribution, meaning the level 1 variance term is gone. It's not that the model's perfect, it's that the variance is determined by the mean in those 2 cases, for instance, Bernoulli and Poisson. So that makes it tricky to do multi-level models that are supposed to explain level 1 variance when it can't actually go down. Link function. This is new. This is brand new. To those of you who have never had me before, but for those of you who took my version of latent trait, this is not new. A link function is a transformation of the model predicted outcome so that the predictions stay within the boundary of the possible outcome. This is not transforming data. This is not. You will not do anything to your data other than to tell your program which link function to use. So that's a big misconception. It's not transforming data. The model itself is transforming the predicted outcome into something that we can fit a linear model to. So what we'll see first is an example of this for binary. Binary outcomes, 0 or 1, that's it. The outcome that the model is trying to predict ends up being the probability of a 1. That's the conditional mean to be predicted by the model's fixed and random effects. Probability ranges from 0 to 1 continuously. We need some way to tell the model, hey, don't predict any outcomes below 0 and don't make any outcomes go above 1, okay? There are 4 different link functions that accomplish that. Logit, probit, log-log, and complementary log-log. There's probably more than that. But that's the big picture. It's like, okay, let's reel this thing in and keep it within the boundaries. Counts, for instance. Can you have a negative count of events? Like I've been to the hospital negative 14 times. Nope. What's the smallest count of events you can have? 0, right? Most of the time. But let's say that you have a data set of hospitalizations, right? What is the fewest number of times that somebody could have gone to the hospital in your study? If the data set came from the hospital, 1, right? You won't have a 0. So in each of those cases, you need something that tells the model, hey, don't predict any counts below 0, okay? And it turns out, if you predict the log of the count can go on to negative infinity. But when you unlog it, exponentiate it, reel it back into the predicted outcome that you have from the model, it stays above 0. There's other link functions, but those are by far the most common and the most applicable to most outcomes that I've seen, at least. But this is the idea, is it's a way of transforming the thing that you're predicting so that when you back transform it into the scale of your actual data, it stays within the bounds it's supposed to. That's what a link function does. We have never had this conversation yet because the whole time that we've been fitting general models, we have been using what is called, in stats terms, the identity link. That's stat way of saying times 1. Meaning, we don't have to worry about this if our outcomes are actually continuous. We don't have to reel them in because they can go from negative to positive infinity. So that is saying that all the models you know are a special case of these with a link function that says, leave it alone, okay? Identity is one of my favorite stats words. Also, you will see something called unit variance. Have you seen that before? Unit variance means 1 also, because we couldn't just say 1. right? We had to call it identity or unit or something like that, but it means 1. So finally, the red part, this is the one you know already. It's called the linear predictor. I used to call it model for the means, but I can't really use that term anymore because it includes the random effects. Linear predictor is how each observation gets a predicted value. It looks just like the models that you've seen already. The only catch is that we're going to be predicting a logit this or log that instead of the original outcome, but it functions exactly the same. It's the same one-unit change language that we know and love. You can have main effects and interactions and everything you've already learned, still true. Only one small catch in terms of estimation. It used to be that in our normal models, the fixed effects didn't have to get found as part of the maximum likelihood algorithm. Once you know your variance components at a given iteration, there's a formula by which they just fall out. They don't have to get found. That is no longer true in these models. So when you add extra fixed effects, you are adding extra complexity. This used to be when you add extra random things. So keep that in mind. I used to say, like, I've had this question before, how many fixed effects can I have? How many predictors can I have? And I'd be like, all of them. That is no longer true. So fixed effects potentially can break models. Random effects are still much more likely to do so. So there's their story. The level 1 distribution, after we factor out the fixed and random effects, is some kind of not normal. We have a transformation of what the model is trying to predict to keep the predictions within the bounds of the outcome. And then we can go predict it using the same stuff we already know how to do. Cool? So why do any of this? Here's a straw man case. Let's say that you're like, screw that, I'm just going to do proc mixed on my binary outcome. It'll be fine. Well, we'll have a single level example in this case because the multi-level stuff all happens the same. So what if we tried to fit a linear model, a general model, to a binary outcome? Well, what we'd be doing is trying to predict the probability of one outcome versus the other. I'm going to say it's the probability of a 1 because I'm used to thinking of things like predicting higher in the variable. So if we were to have an empty model, here, I'm going to try and cover my computer screen for you. That's not going to work. Take all that stuff away. If I just had beta 0, fixed intercept is the expected outcome when all the predictors are 0. If I don't have predictors, it's the mean, right? What's the mean of a binary variable? Proportion of people who have a 1. So that's what we're trying to predict. The stats term for that is conditional mean. So even though the data we've observed are not probabilities, what we're trying to predict is a probability. We're trying to predict the probability of a 1 or a 0. You got to check with your software to see which one it's doing. The default in SAS, for instance, is the 0, which drives me batshit. It's 1 in my world. So I changed the software defaults to make that happen. So if we fit a linear model here, beta 1 would be the change in the probability of a 1 for every 1 unit change in the predictor, difference in the predictor. And E would be how far off the actual outcome is, which is 0 or 1, from the predicted probability. So what could possibly go wrong? Well, number 1, it's a linear model. Lines keep going. So if we have a continuous predictor that has a positive relationship to my binary outcome, that model says that at certain levels of the predictor, you can have your binary outcome go below 0 and above 1. Can't happen. What we need is a model that understands that the prediction, the predicted outcome, the predicted probability in this case, has to shut off. The predicted probability of a 1 cannot go below 0, and it cannot go above 1. Can't. So we need to take our line and, like, squish it like that. And that squishy line right there has a particular name. What does it look like? Do you know the name? You do. Starts with an L. I'll take log linear. I'll also take logistic. In IRT world, it's called ogive, like a normal ogive curve. Squished linear is really the idea here, to keep in mind the boundaries here. So some genius, like a million years ago, and I don't know who it is, but I'd like to give that person credit if I ever were to learn, invented this thing called a logit, and it totally fixes it. So if we start with the probability of a 1 as the thing we're trying to predict, the conditional mean to be predicted, one way of expressing that is as what's called an odds ratio. You take the probability of a 1 divided by the probability of 1 minus probability, which is the probability of a 0, and you end up with something that is hella skewed, so it can go to positive infinity, but it stops at 0. That's not going to help, because then my line needs to be squishy on one side only. But if you take the natural log of the odds ratio of the probability of a 1, that totally fixes it. So this is called the logit. It is also known as log odds. I once had a fight with a former graduate student about the correct pronunciation. He insisted that because you take the log it, it's the logit. And I thought, you know, I can't actually tell you you're wrong, because that makes a lot of sense. So I will accept logit, logit, or log odds. Any of those is fine. Thing that makes it bendy is also fine, by the way. Thing that makes it bendy, the generic term is link function. This is one type of link function that's available. So here is a mapping of what it looks like from probability on the y-axis to logits. So for instance, if I have a probability of a 1 of 0.7, then 0.7 divided by 0.3, that is an odds of 2.33. I take the natural log of 2.33, and that is 0.846. The probability then of getting a 0.3 instead is negative 0.846, and that's why it's so awesome. The thing is balanced, it's symmetric. So at 50-50, the logit is 0. The probability then of 1 is the mirror image of the other. So in this case then, probability of 0.9 corresponds to a logit of 2.2. Probability of 0.1 corresponds to a logit of minus 2.2. Can you guess what a probability of 0.01 would be, given that a logit of 4.6 goes with a probability of 0.99? Negative 4.6. They're exactly the opposite. And this is a big damn deal, because some software packages are going to give you something called a threshold, which is the log odds of the probability of a 0. And some software packages are going to give you an intercept, which is the log odds of the probability of a 1. And those two things are the opposite of each other. So if I have a model that is predicting the 1, the intercept of predicting the 1 is logit of 2.2. The threshold of predicting the 1, meaning it's predicting the 0 instead, is negative 2.2. So this makes it hard to understand necessarily what your software is giving you, but you can always estimate an empty model, get the mean, and see if it's positive or negative, and then you'll know which way it's going. So we're going to have our friend logit make us a squishy line instead. And that's how I generated the picture on the previous page, in fact. The picture on the left here is a logit slope, a slope predicting the logit of 1. When I unlogit and I go to the probability here, it makes it bendy. Unlogit, the technical term for that is inverse link. So you will see that as another term that's hard to keep track of. So I say logit and unlogit because that's how I think of it, because you start from probability, you go to logits, and then you can go back to probability. Going back to probability is inverse link, or unlogit in my vernacular. So here's another picture that tries to convey why logits are so awesome. The predicted logit can go on forever and ever and ever. But equal distances in terms of logit, like a 1-unit difference, translates to an increasingly smaller difference in probability. It will never go out of bounds. Software sometimes caps logits. M+, for instance, the highest logit you can have is 15. But that's still not a probability over 1. And the lowest one you can have is -15. So here are the 3 metrics by which you will see these models described. Probability is at the top here, where 50-50 is sort of the middle agnostic point. That corresponds to an odds that looks like this, where 1 is the agnostic point. And that corresponds to a log odds, or logit, of 0 as the agnostic point. So probability of 0.5, odds of 1, logit 0, all mean the same thing. All right, that's that. So that solves our first problem. We need a regression line that understands that it needs to shut off at the boundaries. Logit fixes that for binary data. Next problem, though, is the idea of residual variance. In a general linear model, residuals are supposed to be independent. Well, we know we can fix that with random effects, right? If they're not independent, we can fix that. But they're also supposed to have constant variance, and they're supposed to be normally distributed. Well, if I have a binary outcome, then I have a predicted probability based on my linear predictor, my model for the means, fixed effects, and or random effects when we add those in. E can only be one thing if it's 0 as the actual outcome, or E is a different number if the person got a 1. So for any level of predicted probability, you have 2 choices for what your residual is going to be. That's it. So that pile of 2 different numbers is never going to be normal. And it can't have constant variance, because in binary data, the mean and the variance are dependent. So the mean of a binary distribution is the proportion of people that get a 1. The variance is the proportion of people that get it 1 times the proportion of people that get a 0. That's what it is. So there's maximum variability if you're half and half in terms of your proportion of 1s and 0s, and that necessarily shrinks down to no variance if your proportion approaches 1 or 0. So the idea then is that the residual variance that's left can't be constant. It has to shrink as a function of the predicted probability. It will be smallest for predicted probabilities around 0 or 1, and biggest in the middle. So the residuals can't be normal, and their variance can't be constant. The variance is tied to the mean. So it's not that there is no residual variance in these models, it's that it's completely dictated by the predicted probability from the conditional part of the model. So just to review what distributions look like, stolen from Wikipedia, the top here is the normal. Normal distribution is characterized by a mean and a variance, 2 separate things unrelated to each other. Bernoulli distribution is what we're going to use for binary data for our conditional distribution. It's characterized by 1 parameter. It has a mean, and that's it. Because once you know what the proportion of people is that got a 1, for instance, this mean is 0.75. You have to know how many people got a 0. There's no separate variance. It's a function of the mean. And so the likelihood function for binary data is actually one of the simplest ones. It's the probability of a 1, if that's what you got, times the probability of a 0, if that's what you got. And so this thing is Bernoulli. So this is what we're going to use for multi-level models for binary outcomes. Each level 1 unit has one binary outcome, and that's why it's Bernoulli as opposed to binomial, which is another option. So the reason why I'm hitting this probability odds, log odds thing so hard is because depending on where you're reading, this same damn model is written like 17,000 different ways. Seriously. So my preferred way is at the top, logit. Do you know why I like that? Look at the right side of the equation. Doesn't that look nice and happy and familiar? Got an intercept. Guess what the intercept is? Expected outcome when your predictors is 0. The only catch, what does outcome mean? Logit outcome. Guess what beta 1 is? Expected change in your outcome for a 1 unit change in X. Outcome is logit. But everything works just like you think it should. So that's using the link function then to predict logit using a regular old linear model, or a linear predictor in this case. Note what's not here, though, that's normally at the end, in blue. What should go here? Yeah, normally, right? That's a pun, see? What would normally go here at the end of a regression model? Or some kind of residual. It's not here. It's not that we're saying the model's perfect. We're saying that once I know what the predicted probability is, I know how far off it's going to be. Either this much or that much, from 0 to 1. So there's no separately estimated residual variance, which is why we don't have an E written in the model. So this makes me happy, because I can talk about all of my findings using the same types of language that I'm used to, and it makes sense because everything is linear and additive. But then you get to the left-hand side. And you're like, what the hell's a logit again? And then you get predictions where it's like, I have a logit of 1.6. Is that a lot? And then you're like, well, a 1.6 is probability greater than 0.5, I can tell you that much. Like, then you're like, well, what the hell's a logit? And then you're like, am I going to make a poster where the y-axis is logit? Is anyone going to know what that means? No. So then we get into the next layer, which is, well, let's just unlog it, or exponentiate it. If we unlog it, then what we're predicting is the odds. And so you have e to the intercept times this slope stuff, or you can keep the function together and write it this way. I hate odds. I hate odds something fierce. It makes no sense to me. I have a really hard time with the idea that you're somehow multiplying coefficients together. My brain can't handle it. So I will show you how to get odds ratios, and I will do nothing with them, because that is my choice. Academic freedom. No odds. Logits are probabilities only. But people like odds, right? You guys love odds, probably. She's like, yeah. Like, what's wrong with an odds? That is your right. That is your right, your academic freedom. I hate odds. So I'm going to skip over that most of the time and go straight down here to probability. Because I would argue that not a lot of people understand odds well enough to have that be the y-axis on your plot either. But people know what probability is. Even my mom knows what probability is. So the only catch then is that your model looks like this. E to the what? Over 1 plus e to the what? And this version of the coefficients, the e version, you can't talk about a 1 unit anything, right? They don't make any kind of sense in that metric. So the compromise that I end up with is I talk about my model this way, because these coefficients I can make sense of. They behave like they're supposed to. But then to show what the model actually predicts, I take my predicted logits and I unlogit them to get back to predicted probabilities. And that idea of unlogit, put it back into the scale of the conditional mean that's being predicted, is what's known as the inverse link. And so there's your formula for how to go from logits to probability. It is e to the logit, so the stuff in the corner here, that's what your logit predicts. e to the logit over 1 plus e to the logit. That's how you go back. I will show you how to make your software do that for you. And just because this wasn't fun enough, you will also see it written like this, where it's algebraically rearranged with a -1 outside the logit on the bottom that allows you to just stick a 1 on the top. So if I'm typing something into Excel, I may do this version because there's less typing. So those of you who've had IRT, maybe, factor analysis type stuff, IRT models are almost always written as probabilities. But if you want to phrase it as a linear model, where you have things like factor loadings and intercepts or thresholds, it's written as the top. It's written in logits instead. 6 of one, half dozen of the other. And that's how you can end up with A and B parameters, for instance, in IRT, that become thresholds and slopes, factors loadings, in IFA or other kinds of measurement models. So that is to say, everything on this slide is the same thing. So you just have to keep track of what is on the y side. Are you predicting a logit, an odds, or probability? And all of these, by the way, are natural logs. There's no like log base 10 or base anything else in this. That's not a thing. Not a thing we ever use, I should say. Okay. Do I want to do this? Yeah, maybe. All right. How are we doing so far? Okay. This might be a little new, and maybe it's something you haven't heard in a while. But are you okay? Okay so far? Ish. Some are more okay than others. I'm okay with that. I'm okay with variability. So here's the 18th version of the same model, written yet another way. This stupid Y star thing. You will see this also, where Y star is the latent variable that you actually have, that your observed variable is the representation of. So like you have some kind of latent continuous thing that you measured poorly, and what you actually have is zeros and ones, but you think of it as an underlying continuum. Well, if what you're predicting is the underlying thing that's continuous, not that you can find it or see it, by the way, it's total bullshit. It's just a representation. Then you get your E back. This idea of an underlying continuous distribution dictates what the variance of E is in predicting this. So if you're predicting Y star that you believe has a logistic distribution that looks like one of these here, also stolen from Wikipedia, then E variance is 3.29. That comes from pi squared over 3 from the logistic distribution. So you will see this number show up a lot in place of what used to be level 1 residual variance. If you're predicting Y star that you think has an underlying logistic distribution, then the E variance that goes with it is 3.29. Doesn't mean anything. It's just setting a scale for what the parameters mean. An equally valid scale is set by assuming that it's not a logistic pretend distribution. It's a normal pretend distribution, damn it. Can you ever be right or wrong when you're talking about pretend distributions? No? But if you're willing to say, no, I don't like that scale, 3.29, that's weird. How about I switch it to be unit variance instead? That's probit. So here's another type of link function that you will see in these models, probit instead of logit. The way it works is a probit is a z-score. It is the z-score that corresponds to the predicted probability area of to the left in the standard normal curve. So if you have a probability of 50-50, your z-score is 0. Z-scores that are negative mean it goes that way, mirror image, and z-scores that are positive go the other way. What's the biggest z-score you can have? Positive infinity. What's the smallest z-score you can have? Negative infinity. So when you back translate Z to probability, it gets bendy and shuts off, just like our friend Logit does. Same principle, just a different scale. The variance of the pretend underlying trait is 1 instead of 3.29. And do you need to give a shit about this? No. Absolutely not. Because these things are just versions of each other on a different scale. So let me put it this way. Would you lose any sleep over the difference in prediction of that red line and that black line up there? Maybe somebody would, but that somebody ain't me. It's not happening. So if you multiply your probit coefficients by what turns out to be a constant of something close to 1.7, 1.71 something, their predictions are identical. So that's what's known as a normal ogive model in IRT world. That's what probit is called in there. And there's no odds ratios in probits because it's not based on odds. So it makes it harder to unlog it. It makes it harder to go back to predicted probability. Otherwise, probit and logit do the same thing. So 6 to 1, half a dozen of the other. Probit was first. Somebody figured out that logit works just as well and is easier computationally, and so that tends to be used more often. Certain software packages may restrict you to one or the other depending on what kind of model you have. So for instance, if you're doing item response theory measurement models and maximum likelihood, you can use either logit or probit, but if you're doing them with a limited information, W, LS, and V, that's probit only. So just 6 of one, half a dozen of the other. You got to know which one you're in to know what the scale of the coefficients is. And just in case you thought, well, that's not enough, I need more of these things, here's 2 more. And gun to my head, I can never remember which is which. There's log-log, which I have written here, is for outcomes in which one is more frequent. So this is for proportions that are highly skewed one way or the other. So watch what happens here in predicted probability transforming into this link. For the right half, it looks a whole lot like logit and probit. The left half, it kind of just like, and it shuts off, but it doesn't shut off with as much curve. It's asymmetric here. That's because in these outcomes, there's not going to be much data on this side, so it doesn't try to estimate the same shape of a curve because there's a lot less information. And the same thing happens then in reverse for this thing, the complementary log-log, which is for outcomes where most of the information's on the left side, not a whole lot of cases on the right side, and so it just sort of withers off here too. So that's what those are for. They're on yet another scale that has to do with pi squared over 6 for some other distribution. I haven't seen a whole lot with log-log and C-log-log. Those are options in software that I wanted you to know about. In the first example that I have with binary multi-level models, just for the heck of it, I tried our last model in each of the 4, and you end up with different answers as to what's significant or not. And I'm not really sure what that means, but that makes me very squishy whenever that kind of thing happens. So just know that these are what they're for. Logit and probit assume symmetry. So the shape of the curve is the same either way you move away from 0.5, whereas these ones don't. And they're made for outcomes in which symmetry is less plausible because there's less information on one side than the other. And there we have it. So, big picture then. 3 parts of the models we're working with. Everything that we learned so far, plus conditional distribution is going to be some kind of not normal to match whatever the outcome is. And we have this link function thing that keeps our predictions within the bounds of the outcome. Within 0 or 1 for predicted probabilities, between 0 and positive infinity for things like counts, and so forth. Yeah. Questions? Brief survey. How many of you have worked with M+ before? How many of you have not? Half and half. Okay then. So that will help me know what to emphasize. But all right then. So what we will have then next time is an example using binary data, and we'll look at the inverse of the cluster data example that we had before. Rather than math, we had free lunch predicting math. Now we're going to have math predicting free lunch. Why? Because I can, right? I don't have a lot of binary outcomes, because you already know the data set. So that's why. So that's what we'll do next time. Office hours start now.